Okay, now we have just getting ready to have Mr. KD4Z give a talk. I'm going to tell you a little bit about him before he gets up here, before we get him started. I've had the pleasure of working with him for several years now, and I have learned that he is a master at programming and electronic design. He graduated from a school in Central Florida with an electrical engineering degree, and he is quite talented. He has been a teacher for me, and I realized fairly quickly that I knew about 1/100th of what he did. So it's been a lot of fun working with him. And I think tonight is going to give you a really good introduction to how to design cars and what process he's gone through to design these boards and these different projects. He probably has, I don't know, 15 different projects going now. So it's he is very experienced in doing this and can, I'm sure, answer any of the questions you have. So with that, you've got your.
We've got to do okay, well, the audio is working.
By the way, it's Warren Merkel.
A little hot.
Want to know his name.
Warren Merkel, that's me, KD4Z. Let's change a few things around here. Okay. How many of you like electronics? Kind of a bold question in a group like this, but you probably realize that just about everything you own that is electronic has a circuit board in it of some kind now, because it's been years and years since we've seen equipment that's put together with old style terminal strips and bits and pieces of wire wired on a bottom of a metal chassis. But so what we have today are boards which are made from copper, and this is a sample of a single-sided, I don't know if we can be able to see that, copper board. This one is fiberglass and has only one side of copper. So this is what it starts out with to be, and then I'll just pick the small one up. This is a double-sided board. So it's just a thin layer of copper on each side, and there's usually some sort of fiberglass resin material between the two layers. And this is just a case of two-sided. We'll talk about that in a second, but all the parts that are wired together use circuitry that is put on these boards. So things have gotten smaller since we started this. So what I'm going to show you tonight is a suite of programs which allow you to design these boards. Those of you that had any electronics hobby as a background of electronics, you've probably scribbled schematics on the back of a napkin in a restaurant and went, okay, now what do I do? You go home and you try to put it together, and you may even have a solderless breadboard, and you build it, and then you go, now what? How am I going to get this off the breadboard? So you cobble it together, maybe dead bug style is a way that people used to do it. You just lay the parts maybe on a piece of plastic, and then the wires are just wired in the air from pin to pin. And it works if it's a small circuit, but what if you got a complicated setup or you want to make more than one? So that's what happened to me. I wanted to start making some things that are more complicated. And I learned to use a program called Keycad back in the late 80s that does the same thing. And it was also free if you didn't want to build too large of a board, but it was awkward and I never really did much with it. So I ran into Keycad about 4 years ago and thought, well, let's give this a try. Let's see if I can pick this thing up here. So what Keycad does, it's like any computer-aided design application. It allows you to do things faster and more accurately, and it looks for errors and things that you might not notice. So Keycad was started by an electrical engineering professor in France who wanted a tool for his students to be able to use to design boards. So he actually started working on this at night and came up with something over time. But he worked on it by himself for about 12 years before he decided to upload it to a site called SourceForge and open it up for help for the world. And that's when it started taking off. So it's an open source program, and they've got it so it's compiled for targets for any OS you probably have. It runs on Windows, it runs on Linux, it runs on Mac OS. So pretty much covers everything that you'd probably want to run it on. And it's free because of that. So you've probably seen circuit boards, you probably haven't taken a really close look at them. You can come up after the presentation and look at some of the boards that I've made here and see exactly what we're going to talk about. But over the years, it started with parts that have wires on every little piece. Those leads end up having to be soldered through, threaded through holes and soldered on the board. The board is just patterns of copper that complete the circuit. So until about, well, I'm not sure when they started doing a mass production on surface mount. The military started doing it first, but surface mount made all those holes go away. So the parts actually just live right on top of the board or the bottom, and sometimes both. And they work the same, they just don't have all the little wires coming out. So we're going to look at the way those boards are designed too. But you can do both with KiCad. As a matter of fact, you start with the schematic, and then however you describe those components, they could either be a through-hole part or it could be a surface mount part, doesn't matter. So yes, we've talked about this already, but most of the boards that you might want to experiment with are double-sided. You don't really need more than that just starting out. It allows you to do just about everything you will need, because you can make bridges or vias between the layers and jump around things. So if you have two traces that want to cross and you have no other way to route it around, you can actually use the bottom side to do it. So it allows you to get more dense with things. But things like in your computer now, the motherboard in a computer could have 8 or 10 or more layers sandwiched in there just to get everything crammed in there and wired, because the processor and the memory chips, the FPGAs now have hundreds of pins, and there's no way to get those all brought out and connected on just 2-layer board. So they make boards by sandwiching them together like a Dagwood sandwich. They build them inside out, and then you end up with a stack that's pressed together, and you have all these different layers inside, but they build it inside out by putting those inside traces. They cut those traces first, and then they assemble it. So if you have about a half an hour, there's plenty of YouTubes showing the fabrication facilities that make these things, and it's amazing just to watch what they do and how they make these things. So for you'll probably only use 2 layers, but those extra layers, I mean, there could be 20, 30 layers if they need it. And they use those to an advantage, at least in RF or boards that have high clock rates for ground shields between layers. So you can have signal layer, then you could have a ground plane that's nothing but ground, then you can have more signals, and they can stack that up and isolate the traces. And also it provides a handy way to get your power rails all throughout your circuit across the board without having to jump around things and put jumpers and go between 2 layers. You can just devote a whole plane to the 5-volt rail or the 3.3-volt rail, and of course ground. So here's some pictures of through-hole boards. The one on the left is an actual board that I made about 3 years ago, and it looks typical of what you've probably seen over the past couple decades. The magnified picture on the right shows how the holes are actually plated through. If you look really close in the center of that hole, you can see it actually has solder or a plating of, through it. And so if you soldered something, okay, I didn't need to do that. If you solder on the top side and you have a trace coming from the bottom side, you're good because it's connected on both sides. If you look closely here, you can see here's a trace that's coming around, but it's not touching this hole. So this is just another trace going somewhere else, but this really isn't connected to anything on this side of the board. But this is, and see, here's a trace coming in there. So that's how that would be. Now, surface mount takes it to a new level. This is one I did not too long ago, but I had plenty of space to put parts on because I have connectors that are large, and that's usually the limiting factor. And as you can see, some of my things I have here, I've just jam-packed things on the edges of the boards because the connectors are always going to be bigger than the parts. So this board has tiny parts on it, but it has lots of space between them, but I could have made that a lot smaller if I wanted to. Now, once we get into the program, first thing we're going to have to do is draw a schematic. So you're going to have to get used to identifying symbols on a schematic, and they're pretty much internationally standardized. There are differences between certain types of components, but the old school styles still work. And if you look at this particular diagram symbol here, this is a transistor. You can tell by looking at it that it's an Ndn transistor. And if you see what you can see around the top and around the side, you see the wires or the leads coming out are marked for what those particular leads are, the base, emitter, collector, but the numbers are important. So the number 1 is on the emitter. So we'll expect to see that connection when we drop it onto the board layout. So we know 1, 2, and 3 go to where they go, and that's how it keeps track. So the symbol has these number designations on the pins, but this symbol doesn't dictate how I'm going to call it a footprint because we're going to learn about that next, and that's what it really looks like when it lands on the board itself. And because transistors come in all kinds of different packages based on power or style or frequency, you have to have all kinds of different footprints to support those. So this symbol can be representative of a transistor, but the footprints can be completely different. So here's 3 examples of that for a typical transistor. The one on the left is well, these are both, the left and the middle are the epoxy style type, tiny little TO92s, and they're just 2 different styles where the pins are either in line or they're offset a little bit. Let's don't do that. And here we are. So right here, this is preferred. This is really hard to solder. So if I were you, I would not use this package when I would laid out a transistor because I found that out the hard way. So this works just as well. This package is a TO3, and it's usually found in power applications. It's really, if you look on the back of your power supply, if it's an older Astron or something, it has at least 1 or 2 of these on the back of it. And what it has is the collector is all the metal can, and it's considered pin 3. And then these 2 pins are the base and emitter. So the numbers are important. Also, think of it as a bird's eye view. When you're looking at these footprints, you're looking down at them at all times. So if you trying to figure out whether it's one way or another, just remember they're always drawn, so it's a top view. So going to surface mount footprints, they look a lot different because you don't have any holes. And if you see the red spots here, those are the pins that would be connecting to the rest of the circuit from this particular device. And so that's where they get soldered, but there are no holes through the board. So it just sits on top. And the way they actually do this now is solder is deposited on those little spots mechanically, and then a machine called a pick and place will take the parts and stick it on there at high speed, and then they run it through an oven and they actually bake it. And they raise it up to a certain temperature depending on what the solder type is, and the solder will flow and the part that just goes whoop, and solders right down on the board. It's pretty interesting. There's plenty of YouTube videos that show that too. You can actually do surface mount yourself. If you don't have too many to do, you can use a hot air reflow type system, which just it's like a hair dryer with a pointed tip on it. And you can do this kind of soldering just by running it around in a circle carefully, slowly until the solder reflows, and you'll see the part go right down to the board. It's kind of interesting. So you have to have a reason to make a circuit board, don't you? I mean, you wouldn't unless you're going to make a business card out of it or something, or make a Christmas tree or something with a bunch of LEDs on it. You kind of need a plan. So I decided that for this presentation, I'd make something you guys might actually want. So I thought about it and thought, well, you know, IoT is a pretty big buzz phrase nowadays. You're constantly thinking, how can I remotely turn something on from the internet? Or I might have an Arduino and I need to control something with the Arduino that's not just low voltage. How do I do it? So I thought, let's make a board that buffers the logic level outputs you would have from a microcontroller like an Arduino would have, and or a Raspberry Pi, and allow it to switch a high current that could be something like your HF rig would require over 20 amps on transmit. Certainly you can't just drive that with the IO pin on an Arduino, or you'll let the magic smoke out. So we'll blow through these requirements. You kind of have to write these down. You have to think about this. Some of the engineering comes in. You have to think, okay, the IO pins, that's where I'm starting from a microcontroller. It's usually nowadays around 3.3 volts. The Arduinos are still 5 volt, but you need to know what that is, and you need to know how much current those pins can actually sink or source, which in this case, it's between 17 and 20 milliamps. That's on a pin, and if you do that on every pin, you'll probably overheat the chip. You can't do all pins that way. So you have to consider that is where you're starting, but clearly we can't turn on even a relay with that to turn on your radio power if you want to remotely control it that way, without something like a buffer in the middle. So let's make something that's got an isolation between the two. So you start out, the left side represents your controller. You've got about a 3.3 volt signal, and you want to control something that's 12 volts with a huge amount of current. So a good way to do that and provide isolation at the same time is with something that's known as an Opto Isolator. And if you look at the symbols, you can see inside it really has only 2 active parts. And on the left, although it's not properly drawn, that diode is actually a LED. And usually you have little zigzag arrows showing that it's a light emitting diode. But in this case, it's kind of understood. It's a light emitting diode in a package with a special transistor that really doesn't have a base connection that you use, but it's designed such that when the photons from the LED come to that transistor, it saturates and turns on. So you have isolation from the left side to the right side of this little package, and it's high. So this is good. This is a good start. But when you look at the specs for this Opto Isolator, you realize, well, that little transistor in there has a maximum current rating that you can't go over, or it will not function very long after that. And so we need to buffer that too. So it comes down to multiple steps to get from where we started to the end. So we start out with the Opto Isolator, and we need another transistor in the middle, because if you look on the spec sheet for this particular opto isolator, we can do about 50 milliamps. Here, our end goal is over here. This is a relay. This is the coil in the relay. Look at that number there. That's more than what this transistor would have been able to supply. So this transistor can handle approximately 200 mils, and we'll stick that in the middle, and that connects all the dots. So going to a real circuit, this is what I would scribble down. It's pretty much all that we just talked about, with a couple extra things that you just glue it together. LEDs are current devices. They'll happily allow as much current as you can give to them through them if you don't limit it. And so this is a current limit resistor, and you calculate that to keep the current low enough to turn on the LED, but not overload what you're driving it with. In this case, this is coming from your processor. So it's just Ohm's law, and it's pretty commonly somewhere in this range between 220 and 470 for a 5 volt to 3.3 volt. That gives it about a 20 milliamp drive. And in this case, this LED actually let's see, it goes to about, I think, 70 mils in the package that I used in this kit. So you got a lot of leeway here. Usually LEDs blow up above like 25 to 30 milliamps, so you don't really drive them that hard. In this case, we're okay. And here's that driver transistor we saw, and it's just in line with the coil of the relay, here's our 12 volt power supply signal coming in. And so when this transistor turns on, we get current flow through here, and it raises the base of this transistor, which then turns on our relay. So that's all we're going to do. So now let's talk about the software, because now we need some way to build this thing. So it's actually at least 2 major programs in one, and then there's some ancillary things that allow you to work with libraries of parts. You need to have libraries of the symbols, and you need to build some libraries of the footprints, but it comes out of the box with a very large library to start with. And there are actually other vendors that have free libraries you can install too, like DigiKey has their own library with all their part numbers built into the symbols. So if you use their library, life is good, because you'll know exactly what the part number is when you use it. So we'll assume that you've installed it, and this is the program manager window, and it shows you the main portions that we're going to talk about. The first thing that we're going to need is the schematic editor, and then we'll use the PCB editor, the PC board designer or editor, and that's how we actually lay out the traces for the board. But the first thing you have to do is draw that schematic, which is what we just went through. But now you got to draw it in the program so it knows how to use it. So obviously the schematic defines how each of the parts are connected together. Nothing magic about that. But if you don't want to build a circuit board at all, but you still find yourself sketching out schematics from time to time, you can use this just to draw that schematic, because it makes it look pretty, and you can print it in, export it into PDF, and just stop right there if you want. But I suggest keep going. So here's the schematic editor as it first comes up with nothing in it, and now you get the now what do I do moment. So let's take a quick look at some of the icons that I'll highlight that I use, and then ignore the rest of them. So over here on the left, the first thing you kind of want to do is tell it whether you're going to work in inches or millimeters or mils, which is new for this version. I would suggest starting with inches, and that's fine, because you can actually go back and forth. Sometimes you might need to change it to millimeters depending on a part you have that's specified that way, but it lets you freely go back and forth, and it keeps track underneath, so don't worry about it. But there is a reason to do some of these things. In this case, here's another option that I would turn on. It see the cursor is a big cross X there, and it becomes a big crosshair that allows you to line and place parts so they line up nicely when you want to connect them together with wires. These are the zoom buttons. They'll zoom you in and out. You'll want to have a mouse that has a scroll wheel on it. Most do now, but if you don't, you want to acquire one because it makes life really easy to zoom in and out, because in one operation you can zoom in and pan with the mouse. Now this is pretty busy, but it shows the icons that you'll use the most. And this one just gets you back home and gets to the selection pointer. So you actually are just moving a pointer arrow around to select components. This icon brings up a chooser that opens up the symbol library and allows you to find all the parts in the library just by either their name or model part number. They've brought out symbols which are commonly used for power to a separate icon. So you commonly will put ground connections on your ground bus, and that's your return path, but you can choose from a variety of different voltages and different symbol styles in there. This is a wire. This is how we'll actually connect the parts together. It works on a grid, and they stick to the grid location. So it's really easy to connect the things up when you drop them on there. We'll do that in a second. We won't worry too much about this, but you can give each wire, or in their terminology, a net, a name. It does help to do this after you've got the board going, at least on some of them, because when you go into the circuit board layout editor, it paints the names of those buses right on the traces when you zoom in. So if you've got a whole bunch of them stacked up, you can actually see what's what just by looking at the names. And then once you get to a point where your schematic is very busy and you've got a lot of lines crossing, you might want to just use these labels. You can just make as many of these labels, and any label any letters you want to make up for naming, any of the same named labels are automatically connected together for you. So you can jump across the schematic if you want without having to make the wire go all the way through the middle of it. Now I'm going to jump into the other editor. This is the layout editor for the actual printed circuit itself. And we're not really ready to use this yet, but I wanted to show you that there are similar icons, but there are some that you will use first and some of that you won't use for a while until you get farther into using the program. But I wanted to have them in this document so you can come back and look at it real fast. We have this document posted in various places. We will have it on the NARFL site, and I have it also linked from my QRZ page, so you can get it right now. I think Bill's probably already got it wired up. He's shaking his head. So we do have it online, and we'll have a link to the video that we're recording tonight also there eventually. Now, all these items listed here might look impressive or confusing. I'm not sure. This board by default is set up for 2 layers, but the program will actually let you go up to 64 layers if you ever needed such a thing. And they would all line up over here, but you have to have certain layers even to do a 2-layer board that facilitate how things work. So FCU and BCU are those front and back copper. Those are the common ones that you'll be drawing the actual traces on. You have other boards, other layers, which are a part of the system that cover up the traces. Those are the silk screen, the masks layers here and here. That's an insulative layer that they coat over the top of the copper after it's been etched, so that it's not available to be shorted from other parts, or simply doesn't oxidize, because you don't want anything open air on copper. But they also, as part of the process, tin every bit of the copper before it comes to you. So when you look at these samples up here, you'll see they look like they've been soldered, and they have been, but it's just a very thin layer of solder. You can write labels on the board. I recommend doing that. By default, each symbol is going to have the designator, like if it's a resistor, it'll be R, some number, C, some number for capacitors. That's for your benefit, because you won't know what goes in that spot if you don't leave those on there. And I would recommend you move them out of the way so they're not covered up by the part when you stick it in there too, because after you come back and try to fix it, you'll be, yeah, Steve is shaking his head because he does work on repairs, and he's looking at a schematic and never can find R21. So that's what I would do. There's another layer which is called edge cuts. That's this one here. That actually tells the fabrication people how big the board is going to be. All you're going to do is draw a square or a rectangle around your parts for the most part, but you can get crazy and they will cut turns and corners and curves. So you can make a round board if you wanted to. You can make to ease the corners of a rectangular board. If you look at the CPO board that we were talking about earlier, the kit, the W4QO kit that we sell, I made that board. And in order to make it fit in the Altoids tin, I rounded the corners. So it matches the shape of the can and will go right in because of that. Well, enough of that. Let's see what we can do in the program. So I'm going to try to switch into KiCad at this point. And I might have to stop the share and reshare it because I think I shared just the PowerPoint. Okay, sorry about that, folks. So this is the schematic editor, and it's a blank screen, of course. If I can get rid of that. Okay, so these are the menu items that I was pointing out that you'd want to get familiar with. The first thing, though, is everything is very handily available in the context menu from the right click. So I just right clicked, and the first thing I'm going to do is check the grid setting. Now I've got it selected for the 0.05 inch grid, and there's also, you can get to any of that across the menus up here, but that's important because when I come in here to add a symbol, it loads a list of items from its built-in library, and they're mostly designed with that grid spacing in mind. And it will drive you nuts if you choose a tighter spacing and then try to connect a wire to it, and it won't let you connect to it because it's between the grid pins. So you don't want to run into that. And if you do, we have a question. We have a problem.
Yeah, your screen settings in Windows went from being mirror to extended display. And so what we're seeing on the screen that's shared on Zoom is not that screen.
Nice.
But you get that to the desktop and do what we did earlier.
I'm gonna have to stop the share to do that. Okay. It's set to duplicate. Okay, well, how's it look on the camera, Ian? Can we just go with it? Let's try the share again on the application that I have open. Maybe we can pick just the. Now what do we see?
Yeah, that's that. There you got it.
Okay, let's rock. So if I come over here, I'm going to pick the symbol selection here I just clicked on. If you click anywhere in the workspace, it opens up the dialog, and you can just type stuff like if I type a C, the first thing that comes up is a generic capacitor, and if I take that, I got a capacitor on there. I can do that again by just clicking, and it will bring back the picker. And you can see as we go along, it's going to keep track of some of the anything that we've selected, so you can come back and pick things faster. Now I just scroll the scroll wheel, and wherever the cursor is, it zooms in. So you can see I can move around and do things. Now, another thing that is very handy to know is there pretty much has a keystroke map to any function. So if I hover over this capacitor and I right click, now these are all the functions you can do to this component, but the most often thing you might do is move. And see, it's a letter M. And so you'll get used to using the M and the R to rotate it. So if I just hover over this and hit the R, I can rotate it. And it's by default, it's set to 90-degree jumps, but you can change that to 45 if you need to. So move is I'm going to press the M, and I can move that over here. And if I take this resistor here and I'm going to rotate it here, I'm going to select the M. Now you can see because of the grid, these are starting to line up nicely. Now, if I wanted to connect those, this is the add a wire tool, and I just hover over and you can see the crosshair change. If I click, it's going to draw a wire there. So that's effectively connected together. Another thing that you will do a lot is duplicate things you may already have. And let's see, they do change that key sometimes, but here it is, Control D in this screen. So Control D would do the duplicate. So now I can just make a bunch of resistors in a row. And so these are just the symbols, and there's no values attributed to these yet. You probably will need to change that, and we will. So another common key you'll press is E for the property sheet. That's this option here. And I was on the capacitor. So here we were on the resistor. So it doesn't know anything about the resistor other than it's gonna be named something R and then the question mark. And that's we can automatically put numbers in a second. If this is say it's a 100 ohm resistor, we can just put that value in there. But this is where it starts to get a little bit tricky. So if you're going to build a board that just has all through hole parts, you'll want to use just the through hole footprint. So I typed in RE, which brought me down to the resistors. And there's the list of through hole parts. And you can see there's just a ton of footprints already in the library, and whether they're laid down, and these are all arrayed resistors. Let's get down to see, these are axial, these are big resistors. Let's see if I have something that we'll want to use here. This might not be the best section. Let me back out here. Resistor. So this is the tedious part, really, when you are laying out these parts the first time and you pick them from the library. And what I've done is I use a private library that has my stuff in it, and I called it my footprints. So if I was doing something over and over again, I would make a copy of the footprint in my library, and then I can do what I want. So it looks like I'm jumping around here. I just wanted to show you a little bit of how you pick parts and pick footprints that go with them. So I just picked a particular axial footprint for that. And that, if I had decided to do that before I copied the symbol, then they would all have that footprint. But I would have to do the same thing on each one of these. And this is that footprint, blah. So it gets ugly if you don't do some thinking ahead of time. But since I selected this last, it does keep track of that. And so I'm able to pick them rather quickly. So I'm not going to really do much with this circuit, but I wanted to show you that the connections are made this way. If we're going to, obviously may have a ground connection here. So I'm going to pick a power ground symbol and drop that on. I usually use just a simple ground connection like this. And I want to maybe move that over here, and I want to move you over here, draw a few more connections. And we might not have much else going on here. This is going to be a do nothing circuit, but you can see you can connect as long as they're on the grid. It'll let you draw these lines to them. And I'll take this ground and we'll just move it up. And you can see it acts just like any other symbol. When I can pick the wire, you can also do W to start the wire. And it automatically puts a connection dot there if it interprets that as a connection. So you know that those are actually joined together when you see that. There are, like I say, we could do a bus label here. If I wanted to call this line 1, I can put that right there on that connection. So when we get into the PC board layout, this particular trace will show line 1 on it, and you'll know that's what that was. So in order to save time, I'm going to abandon this schematic. We're going to load the schematic that that I have pre-done for the demo. And you know what? I wonder what's going to happen here when I change this. Okay, we might have to go through that routine again when I change. Yep. Okay. So we didn't test this out with Zoom. That's unfortunate. I'm going to go back out and load a prior for the demo. This probably isn't being shared, so let's get that up and going and then we'll share it again. All right. No. Okay. So the little widget that we were talking about before has been drawn in the schematic editor. And if we come here, we can see this is just a terminal block that would have little screw connectors on it. And you can see I've labeled them anode 1, cathode 1. That's because we actually have 2 separate opto isolator circuits here, and I've just labeled them for convenience. Here's the driver transistor, and there's that current limit resistor we needed for the LED there, and we have two channels because we're going to have 2 different relays driven with this. But these are just the drivers, and you can see here's one of those connection labels, K1 coil, actually comes down here to K1 coil. So that you can imagine there's a wire actually connecting these 2 points. They're on the same network. Here are the terminals that we're going to use. They're just big holes that we're going to put 7/16" bolts through, and you can stack the ring connectors on there to connect the power leads in. If you need power poles, you can build yourself a little harness to change it to power poles. Since my power supply uses the big ring connectors, that's why I designed this to be that style. So these are the relays, and you can see they kind of look, sorry about the jumpiness here. They kind of look like what they do. There's a coil and that pulls in the contacts, and when that pulls down, the switch is closed. So the positive side comes through here and ends up over here. So our load would get power at that point. Now, the nitty-gritty stuff, and I'm wondering what's going to happen to the share. I'm going to have to swap to the share. I clicked the button here in the top corner, which is launching the PC board editor. And it is not showing. Let's see. first time you go in, it needs to have a file to utilize for it. And I bet we need to reshare. Okay, we good? So this is obviously a blank screen for your layout because we don't have any parts here yet, but because we drew the schematic, it knows what we're going to need to do. And it has, let's see, this is new. We're looking at the version 6 of KiCad, which just came out 3 weeks ago, and they've changed all the icons on and they've changed some things around. And I wanted to make sure that I showed you what you would download if you went and got it tonight. So there's only a few things that matter that are different. So once you're here, there's an icon up here that drags the net information and the symbol information from the schematic, and it will bring them all over into here. And this represents all the footprints that I have assigned for each of the parts. And it doesn't do you many favors. It just lumps them all in a big pile. But if you look at these, you can see, well, that's a relay, that's a relay. So I'm going to start just grabbing a few of these and moving them out of the way. So I'm going to hover over that relay. I'm going to move it up and out and move this out here. And we don't need these. These are the DIN rail mounts that I've provided for, and they're just holes. So you can mount the board on a DIN rail system. These are obviously our terminals. Whoops, I didn't need to mean that. So I'm just moving the mouse over one of the footprints at any given time, and I'm pressing M and it will move. So if I select that footprint, I can move it out of the way. So I'm not going to do a terrible job here. I just want to show you that it gets tedious because you kind of have to have an idea what you want to lay out on the board. So I would start with maybe the terminal block here, which we pick up, and I would move it to, say, the left side of the board. Now I can use any of this workspace I want until I actually draw the outline of the PC board. I might just grab some of these and move these out of the way. But you can see these wires are starting to have these little sticky things. These are called rat nest wires. And what they are doing is they are showing you that that terminal has a connection to this pin on this footprint here. So these are actually need to turn into traces at some point. And if we want to do that, I'm going to show you the finished board so I don't have to make this pretty or anything like what we want to use it for. But we're going to come over to the toolbar, and here's the routing tool, and it allows us to draw the traces between parts. And first thing we want to look at is right here is which layer we're drawing on. The little caret tells us we're pointing to the F copper, which is the front top layer. So we would end up with a trace from one to the other. And that actually is a very small trace because I haven't set up the actual classes to define these widths, but there's a whole setup screen here, which will kill too much time going through, but you can define the traces, the widths that you want to use, the sizes of the vias you want to use, and how many layers actually the board uses. And if you turn off some of these other layers, it doesn't get as complicated. I opened a dialog box. Interesting. Well, this is going to be fun. So, okay, so interesting. Okay, so it looks like I won't be able to open too many of those screens. So if you can see that this part might take some time. I'm going to, yeah, I think I can do this without changing anything. The edge cuts layer is the layer that we ultimately would draw. So draw the board. If I was going to try to fit it on a board this size, I would I'd pick a line on the edge cuts layer, and we can draw the board outline as such. and this is just random. I'm just going to make a box here. It's not even square. But this line outline would become where they would make the board. And if you don't have the parts or footprints inside that spot, it won't be on the board when they make it. So we would want to move all these parts into a board size that you want to have. And typically they charge you for the size based on the square inches of the board. And for American fabricators, it's about $5 a square inch, and you get 3 boards for that. That's from the Osh Park people. You can do considerably better if you send it to Chinese fabrications. And even though you pay more to get it delivered, the boards themselves are 1/10 of the cost. So it comes out better that way. Just because we're having the technical problems when I open the painters, I'm just going to have to jump out of this and go into the final. I want to show you the final design, and then I can move some things there a little bit at a time. But this is not going to be fruitful if I can't jump in and out of these. Yeah, so let me go out and open the final project. And reshare the schematic on that. Now, astute observers might notice that this part wasn't on my schematic the first time we looked at it, on the one that I drew on the white graph paper, and that was because of this time, the supply chain problems. Sometimes you pick a part, and by the time you go to fabricate the board, the part's not available. So you have to drop back 10 and punt and find another part. So that's what I had to do. This is an Opto Isolator, but it has 4 of them in the same package. So I only needed 2, but I actually have these parts in my stash of parts. So we can make these kits with this part. I chose it for that reason, but I ended up having a couple extra sections here. So I thought, well, if I add another terminal and appropriately pick the limit resistors, I can give you the ability to drive this with a 12-volt signal too. So a lot of radios have a 12-volt switched output that turns on when you turn the radio on. You could feed this with from that signal and then turn on something else like an amplifier or the rest of your shack. So it's versatile this way, and they just are what's known as wire ORed together, and they both drive the same 2 relays. The rest of the circuit is the same. I want to show you the diagram, but it's going to blow the screen share. This is, let's see if I reshare it or not. Do you see the layout, or you still see the? Yeah. Ooh. I have to stop the share. Where'd it go? There's that. Share. Okay, guys, sorry about that, but here is the final layout that I went through and did. Now, there's many hours probably involved in what you're looking at right here, and I'm not gonna lie to you. This takes time. You have to have patience, but you can do just about anything you want with this application. And what I've done here is laid it out on a board as tight as I can with those connectors spread across the bottom so the wires come off the bottom. And the traces are actually copper fills instead of being just a thin trace like these. See that the layers here are in different colors, and that's what these icons mean here. On the right, you see the layer red is the front, and then the blue color is the back side of the board. So you can see those aren't actually touching, they're on different sides of the board. And if you have a multiple layer board, you'll have a color for each one. I don't recommend going past 2 until you've done a few though. So what I've done, since this is a high current path, I not only drew in the trace to wire the connections from the common pin from your battery, your power supply coming in, I widened it as wide as I could, and this is all solid copper here, and it's also on both sides of the layout. I can flip that around. This is the backside view now, and you're looking at it the other way. So I've used vias, that's what these little bullet holes are, to connect the two together, so they act as the same trace. And I've done even more than that, which I'll show you in a second, which is something very neat, but it's not going to share well until I stop the share again. I didn't realize that it's going to do this to you folks. There is a nifty 3D viewer that shows you what you've done. And I just launched that from the PC board editor, and this is what it looks like. So once you're in here, you can do a walk around. You can zoom in and see parts, clearances. You know, if you've got things that overhang the board, if you've got parts that touch other parts, there actually is a referential check that does that for you. But I'm just dragging the mouse here, and you can see I can drive around into this thing and just take a look at anything about the board that I want. And one thing I've done here is I've exposed the solder mask. So this is where you see the yellow color, that's actually bare copper, or it's going to have a solder covering. But if you decide that you don't think these traces are going to hold the current that you want, you could lay like a 12 gauge bare copper wire right across that and run a bead of solder down it and beef it up if you wanted to. But that's what this is. And you can see the white lettering, that's the silk screen layer. So any text you put on that layer, they will print on there. And this is just added text that I put on there signifying the part number of the relays. You can put, you know, anything you want on there, and they'll print it on there. You can also import graphic pictures as long as they're like 1-bit format, monochrome, and put a graphic image on here. We did that for the CPO project board, and we have the North Fulton logo on the back side of the board, and that's all I did was make a footprint out of the graphic, and then you just import the footprint to the layout. It doesn't have any connections to it, it's just on the text on silkscreen layer. But you can see, if I can line it up here a little better, that these holes are truly plated through. Maybe you might have to take my word for it, but you can drill in and see, because when you design your own footprints, which you can do, and that'll happen, you'll find that you have some magic part that you want to put on there, and nobody's made a footprint for it yet. One of the editors in this application is a footprint editor, and you can actually go in and draw your own. And I've done that many times, and you have the ability to put these holes in and on a grid so they're lined up just so. And you can tell it whether the holes have a plate through or not when you do that. And when you're in here, you can verify, see the shiny effect there. That tells me that's actually a plated through hole. So that's what I would want on all of these. Yeah, so I took great pains to label everything here, because after you make it, you forget what all these things do. So I've laid this out. So here are the logic inputs that work out nicely that it doesn't matter whether it's an Arduino or an ESP32 or another chip that uses 3.3 volt IO pins. It works out nicely that you can use this same set for those. And here are the 12 volt inputs. And I don't have, let's see if they are going to view here. It has a mode that shows the parts in 3D as well. And I don't think I've got that enabled. This was a fresh install of KiCad for the demo, and I don't have the 3D models enabled. So once you get into this, you'll find that you can get 3D models for all the resistors, capacitors, relays, anything, and they show up in here in 3D. And as you rotate it, you'll see them in 3D too. So you can see, oh, that's going to conflict with the jack next to it. I can't do that. I'm going to go back and move it. So this is a very powerful screen to go into before you get too far running all your routing between the pins to make sure that they don't touch. And we lost that. So we're back to, let me get back to the screen editor here. So what is this? How do you actually, what do you do to make these boards? Probably a question. I mean, we've got a nice drawing here. So one of the outputs that the manufacturers need are called Gerber files. And each layer in this application creates a single Gerber file, and they know what to do with these. Okay, so I've opened a dialog box that shows a screen that's asking me what I want to export into the Gerber files. And it just has checkboxes for each layer, and it defaults to the well-known layers. So that was from a screen which you can see under Fabric. It's broke the share again. Wow.
I don't know if you got the share back, but got it back now.
Okay, so the share is back. So I won't open the dialog, but under fabrication outputs, this menu for Gerbers brings up a dialog which asks you some questions about the Gerber files. You can take all the defaults out of the box, it'll work. But there are certain layers that they do need. And I've got those listed on that sheet on the PowerPoint. But in general, you'll have to have the front and back layer. I'll point them out over here. You have to have the front and back copper. You'll have to have the silk screen layer, and you'll have to have the mask layer and the edge cuts. Those are what you would have to have for a through-hole board. If you were doing a surface mount board, you have other layers, adhesive and the paste layers. Those also have to go out because of the way they're manufactured. And I know I'm blowing through this, but if you spend some time on YouTube, you can find all this I've talked about in gory detail and learn everything that I've said until it makes sense. And that's how I got started. I found a couple of good YouTubes and then started playing with the application. So those files are they look like text files, but they end up with a file extension of GBR. And you just grab those into a zip file, and you would go to any one of the manufacturers, which I've listed in the PowerPoint at the end, and we'll pull that back up now. Maybe this one. So I've got some a resource page here. This tells you where to get the KiCad application itself. The Wikipedia is actually very detailed for descriptions of what circuit boards are. I would recommend going and looking at that. I learned a lot just looking at it myself. Here's a link to the DigiKey KeyCad library, which is free. You can download it and install it, and you get all their parts in with the parts that came out of the box from KeyCad. I use this site, JLC PCB. It's in China. It's the largest PC board manufacturer on the planet. And they have a pretty easy to use website. I wish I could jump into it, but obviously the sharing is going to be a problem. But you basically take those Gerber files, and there's another file that comes out which defines the holes, which gets generated on another one of those steps in the menu that we didn't get to see. You zip those up and upload that zip, and they show you on their website using the Gerber files you ship them, your board, and you can inspect it and see if it looks like what you want. And they give you the price, and a couple clicks later in PayPal, and they start working on it. And in normal times, you can get it back within 10 days from when you upload it to their site. The boards this board we just looked at, I tried to get done so we would have it tonight, so you could have it to take with you if you wanted to buy the kit. Taken 3 times as long, and it should have been here 2 weeks ago. It'll be here Friday. So, but we're also missing the relays that go on it, which are going to come maybe the second week of next month. So we may have them at the next meeting for sure. If that goes well. If not, we'll just have them at the very next Hungry Hams lunch on Wednesdays. We'll make sure that they're available there if you end up getting one of these kits. So in the PowerPoint presentation, I've dropped the schematic for you so you can look at it and you can see what I was talking about, and a couple shots of the layout so you can see all 3 views that were coming out. This came straight out of the KiCad program. Yeah. So I went ahead and ordered these boards, and I have 20 of them coming that'll be available. So if you would like to have one of these boards as a kit, we'll have a list over there. We'll start one if it's not there, so you can be on the list of 20. We've calculated the minimum cost we can do this is $20. So if I don't think you could buy this thing for that, because the relays themselves are about $10 to $15 a piece if you go buy them at an auto parts store. They used to not be that expensive, but everything is almost doubled when it comes to electronic parts like that right now, if they're even available. And that's the problem with these relays. None, DigiKey, Newmark, all the other normal places that you would buy electronic parts from, they're out of stock, almost everything right now. If they do have it, the lead time is weeks and weeks. So I had most of these parts available from my other endeavors. So we use like the Opto Isolators because we had them, and you'll have fun doing this. And it'll also give you an incentive to maybe play with an Arduino or something else, Raspberry Pi the same way, because that's actually pretty interesting. Because next month, if you'll have me back, I'm going to talk about Node-RED, which is a low-code programming environment that allows you to draw programming visually and make things happen, and you can do web interfaces with it. And interestingly, remote control is a big fun thing now on ham radio, and people have gone crazy in Node-RED designing to remote their stations. I'll show some of that action. My station has got some of that action going on, and it runs on a Raspberry Pi. So you could use one of these boards to turn off and on the radio from just one of the IO pins on the Raspberry Pi, and not leave it running all the time, and just pull up your phone and pull up the little web interface and tap a button and on it comes. So that's pretty much the end of that, John.
Would you say when they laid this board out the first time, to put a much larger board on there in the drawing,
and see how each connection is made, and then start shrinking down.
Yeah, yeah. If we went to the trouble to move all those footprints into a nice shape and layout, you probably then would get an idea how big it needed to be, and then you would draw the board around it. Or if you were doing something targeted that requires you to put it in a specific case, this board was designed to fit this case. So well, they'll see it on the camera. All right. Yeah. Okay. So I have a design. This is a design I did last year. This board inside here is an exact size because this aluminum extruded case has grooves that allow the board to slide into it. So it had to be a certain length so that the end caps could go on. So that was a design that I started with a board size and tried to cram everything on it. And it actually didn't all fit. And in this particular case, I had some LEDs and some extra jacks, and there's a vertical board that is right there. Yeah, very good. It's hard to see. Let me get the light on it. So there's another board vertically there that holds extra parts because I ran out of space to fit it on the board. But anyway, this was a reason you would start with a physical size board and then try to squeeze everything on. Sometimes you need space just to make things work. This is a 2x1 antenna. Well, that works out better. This is a 2x1 antenna switch design that, due to its sheer spacing, helps with the isolation between the two sides. So on the back side is the business end. There's 4 relays, 2 per side, and because they're spaced far apart, we get incredible specifications on this particular design. And this board allows you to take 2 radios and derive 1 antenna, and the radios do not see each other with enough power, even at full power, to hurt the other one. So it has isolation, has almost 100 dB of isolation between these ports, which is about 20 dBm higher than anything you can buy, even at DX Engineering right now. Their best is about 80. So this was this is the 5th iteration of this board, trying to get that specification better and better. And we moved these relays, started them close together, had them at right angles. And this was an experiment that just got on and on and on until we actually got something like this that works really well. But it turns out that the coupling of the coils in the relays were the biggest problem. That's why these relays can be close together. They're not energized at the same time. So if you go to my QRZ page, I have a analyzer scan showing the performance of this thing, and you can see what I'm talking about. This board is designed to work with this kit, which I'm going to eventually get available. There's a bunch of jacks on the front and the back. And what it allows you to do is AB between 2 HF radios at the same time, instantly. It has switching for the mic, the paddles, the foot switch, the speakers, the PTT line in and out for the amp. All of that with a simple switcher, you can go. So if you have 2 radios and you want to compare them instantly, this device switches them back and forth, and all those wires don't have to be unplugged and replugged. So, you know, no one has more than 1 radio, right? So no one needs this. But if you came from the old, audiophile days, and you grabbed your speakers and you went over to your buddy's house and you put them on the B side and switch, and you went A, B, and you argued who's got the better speakers, this is what does that for HF radios. But in order to make it work, you need to be able to switch the antennas too on the backside. So this had to be made to do that. So both radios come in, and then you have 1 output. And one of the jacks actually matches up to this. So this drives this instantly. So it's a system. You can come up and look at some of these other boards if you want. There's some other boards that I've made over time. And if you have any other questions, do we have any questions in the chat? Checking now. There, I see 9 messages in the chat have been listed. Are any questions in there?
You see me?
Okay. All right. So
Yeah, can you see me?
yeah. So if you want to get started on this and you need to get over the hump, just give me an email and I'll see if I can get you going on it. And if you're local, you going to Hungry Ham someday, and I'm going that day, I'll bring my laptop and I can show you some stuff that I couldn't get to during the presentation. But you know, download the program, watch some videos, see if it's what you might want to play with. It might get you back into doing electronics again. You may have done it as a kid, but now this gives you a way to actually realize some of the things that are stuck on that solderless breadboard for 20 years. That's about all I got.
Yeah, hello.
Thank you very much, Warren. That's outstanding. These are really fun exercises. The side benefit, and like he was showing you the relay board, when you figure out you're doing one project and you start doing something else, this little board became an amazing experiment that neither of us thought it was going to end up being. When you start looking at isolation, how everything went on the board, because you were able to do the design. We could talk about how, oh, well, let's put them over here, let's move them down there. And then we could check to see exactly what the isolation was. And it was an amazing learning experience just to be able to do that. And we had no idea that we could have a board that had that kind of isolation to it. So that's the real advantage to being able to do some of these things and get involved in it and just play with some of these designs, because it's not only is it a learning experience, you might actually come up with something that nobody else has or has done.
Mm-hmm.
So, and Warren has become amazing on the design side. So it's been fun to be involved in some of these things. Some of these products are going to be something I think you ought to look at. And this board for $20 is an amazing deal. And it's something you can use on your radios. If you have 2 radios, you ought to buy one of these boards. So thank you, Warren.
Yeah.
Outstanding. And we're actually going to have a certificate for it. We just don't have it tonight.
Yeah, that's
for doing this.
Yeah. And
So
I might add, with that board we talked about, you don't necessarily even have to connect it to a Raspberry Pi. You could just use it as a remote switcher in your car if you want, or in your shack, and just have a toggle switch, give it power. And it's just a low current switching, but down in the back somewhere, you'll have a nice clunk when the relay clicks, and you have a short path for that. So, I mean, you can use it any way you want. So that doesn't have to be remote control.
outstanding presentation. Thank you, Warren.
All right. No questions.
Oh, yeah. Do you guys have questions? You didn't get to ask.
No. Is anybody awake still on the Zoom though? I mean, I probably, I apologize for having to stumble through some of that because of the technology. It works really better when you're just looking at it on a couple screens on a computer, because you can hop back and forth. And what I didn't mention and I couldn't show is you can keep the PC board layout on one panel if you have 2 panels, and the schematic on the other panel, and it highlights between the 2. If you select the transistor over here, it shows it to you on the PC board layout, and vice versa. So you can find your way around very quickly if you have both panels up at the same time. And it's kind of tough with the share. You have a question? Come in. That must be Mike. Is that Mike? Hey, Mike.
Greetings from Hawaii.
Yes. There's two kinds of routers support. It has a built-in push and shove routing mode. I didn't get to show much of that because I didn't get many of the parts laid down, but the push and shove is built in. And if so, you lay down a trace and then you lay down another trace next to it. And then you've got a third one that has to go in there somewhere. And you're like, what do? If you take the third trace and try to route it along, the push and shove will push the other two out of the way for you. It'll actually move them using the rules to keep them a certain spacing, and you get to define those rules. So that's built in. It also has an import and export mechanism that exports a special file format that is used with the free routing Java router, which is freely available, which is an auto router. And I use it usually to jumpstart the complicated designs because it may not be able to do it all, but it gets you going. And it's just a Java application. I didn't put a link to that, but I can extend that on my KRZ page, I guess, to talk about that. But yes, it supports the free routing Java application, which reads the file that you export from KiCad. You run the routing in it, and then you re-export from that and import it back into the PC board editor, and boom, they're all as it was routed in the external router. I would say it's fun to do, and it's gee whiz to watch. If we had time, I'd pull it up and show it to you running. I actually have it on the laptop, but it's kind of magic because if you've got a really complicated design, it sits there and it goes edge to edge, trying all the combinations, and it's ripping and laying down tracks as fast as you can see them flicker. But it could take an hour on a complicated run to finish. But it doesn't always do the best job. So, your mileage may vary, but it will use that.
One thing you can do is go to QST or any place where you can find a rather simple diagram and put that on the program and then see what it does. So you don't even have to come up with your own design. That's a good way to start. And I'm lucky that I'm still living, because I'm the world's worst. I go down to the Warren's basement and say, you know, if we could do this. And that's after he'd worked 15 hours getting done what he'd already done.
Right. This is not my day job, unfortunately. So I knock these out as fast as I can. Something I didn't mention, which is actually an aha moment, which I don't know if we'll still be on the camera or not, but this case doesn't come with caps that have holes in it. It comes with a solid metal plate for each side. You have to drill those holes. Well, John did that the first time and came back really angry, gripey. So he doesn't want to do that again. So I had the brilliant idea of, what if I designed a PC board that just has holes in it and no traces on it that matches what I need? Well, this is that. This is another project that isn't this, but it's in the same case. This is a PC board I designed in KiCad that is nothing more than the front panel of the project. And it's a double-sided PC board. You can get the screen in black so it matches the case. The solder mask is black, and I used white silk screen, so you can put any text and letters on there you want, and they can actually route inside holes, which is what this is. And they have such tiny router bits. That's actually a round corner, but it's so tiny you don't even notice it. So I have a display behind this hole on the project this is for. But this is fantastic because it makes it look like a finished product. John actually drilled the holes in this one.
Yes, his brilliance kept us from killing each other.
So we're not going to do any more of these by hand. I am going to have to design the layouts to do all those holes for this. And then eventually I'll offer this as a kit. All this stuff we're hoping we'll be able to offer is just kits. I'm going to sell the boards, give you the parts list, knock yourself out. And for all the early stuff, it's all through hole so you could still solder them. And anything like this board, which is in the new antenna controller design, this is mostly all surface mount, and it will come already soldered with the surface mount parts on it. The only thing that will be left are some of the connectors on the back and a connector for the display. And there's so few of those, we'll probably just go ahead and solder them and offer the thing completely assembled. Sure. Well, we started out doing all the assembly because it's all through hole. We did the first prototypes all ourselves. And I think it's mostly the supply shortages that got me thinking about doing surface mount too, because the manufacturer I have the boards made through also does SMT assembly as an option. And it's inexpensive. It really is. This board here, it was done by the JLC PCB company. And you have to do some little extra work. You have to define another file that the pick and place machine uses to pick up the parts and stick them in the right places in the right locations. That the Keycad instantly creates that file. It's not a problem at all because it's part of the layout. And when you do this layout here, you've defined where all those parts are and the holes, and each of those footprints has a centroid location defined, and that's where the pick and place machine will pick it up and put it on the board. So this was mechanically made, and it showed up just like this to me. I have not soldered anything on this board yet. So we have, two RJ45s, there's a Phoenix connector that goes on there, and then there's a double RCA that goes on this side, and then a small terminal connector for the display in the front. But that's all that gets soldered, and you can almost finish this in about 20 minutes after the way it comes now. This is another board that has gone through that iteration. This is the actual through hole version of the same board. It has all dips and hand discrete mounted LEDs on it, and there's 16 of them all across the bottom. Well, I've done these now on surface mount, so all these LEDs are already mounted here on this board, and there's a couple chips that I can get, but this one dip is still unavailable in surface mount. You have to use their parts is the thing when you get them assembled that way. But they're cheap. If you buy them from them, they're actually cheaper than buying them here and shipping them to them if they have them. And so they didn't have this part. So I said, I just put the dip package back on the board and made everything else surface mount. And these black things are relays. So those are just on sockets. But everything that I could make on this relay board surface mount, I did. And I think that's the way we're going to go from this point on because it saves so much time. I mean, if you want to build kits, you can buy our CPO kit we made and get used to soldering. But you do some of these more complicated kits like this one, we're probably not going to be able to do surface mount because there's nothing active in this. It's just a bunch of relays. It's really all this thing does is switch things. It does allow audio from your computer to come switch in optionally. So you can use a web SDR to listen to your stations that say are past the gray line and you're in a net in the morning and the band hasn't woke up yet and you have to hear them on a web SDR out of Utah, but it comes back to you and it's time for you to transmit and you're scrambling for the mouse to turn down the speaker because you don't want to hear yourself coming out of the same web SDR and an echo. This mutes it for you. So when you go to PTT, I mute the sound coming in, the audio coming in from the computer. So you don't even know that you're using a computer to receive. It's seamless. That's what the idea was anyway, and it works pretty cool. That was the idea for that. Anything else? Good question. Yeah. Everybody ready to get out your soldering iron? Yeah. Let's make something.
Well, this takes you down to interesting paths. He and I decided we would build an oven to bake all these SMDs. And we actually have done that.
We do.
So you learn that you can do a lot of things you don't anticipate.
Yep.
And it just has, it's a fun experience.
I bought a toaster oven to just sacrifice. So I had the toaster oven and a timing controller, temperature controller for it. John thought another controller was better. He acquired that and then took it on himself to build the whole thing and then brought it back to me done. But he says this is the only one I'm doing. Never do it again. But we have a toaster oven that's about this size. It can hold a board probably about that large. And it has a timing sequence for both leaded and non-leaded solders. So I could bake those boards. We've done some boards which you haven't seen yet. Had Tech Fest actually occurred this year, you would have seen a new kit for the kids, which is a little radio receiver, little FM receiver board. It's only about this big, all through whole parts except for one IC, which is surface mount. And they didn't tell you that it wasn't going to be soldered. So John and I baked, what, 50 of those things already?
Yeah.
We've built 50 of those boards in our toaster oven and it works. So the hardest part is depositing the solder, which is in a paste, kind of in a syringe, in a small amount on each of those little pads. And then with tweezers, taking those teensy little parts and trying to get them lined up on there.
Pretty amazing.
Yeah.
Start here, you never know where it's going to go. I know
Yeah.
we're running.
So we
real
can do
late.
that now.
We're
Yeah.
running late, so we got to close the doors. So,
All right.
You don't have
That's
any
it.
more questions? We're going
We're
to
wrapping up.
move to our final stage here.